In the last lecture, I had started talking about the positive real lemma. Now, I did not give the complete proof of the positive real lemma. In fact, what I had said was when you have the positive real lemma, it gives an if and only if conditions. One set of conditions is in terms of matrices from the state space representation of the system, and the other set of conditions is a frequency domain condition, which deals with the fact that the given transfer function is positive real and things like that. But what I showed in the last lecture was that when the set of conditions that is satisfied by the matrices, when that set of conditions are satisfied, then passivity takes place, in the sense that I showed, we had already discussed in the last class this thing about a system being passive is equivalent to the existence of a storage function, and that the supply minus the rate of change of the storage is equal to dissipation, which is a strictly positive function. And in the last lecture, I showed that when the matrix conditions are satisfied, then we do get some other matrix which is positive definite, and that actually stands for the dissipation function. So today what I will do is I will start first with positive real lemma, and I will give the complete proof of the positive real lemma, and then we will carry forward with the rest of the stuff. So let me recall the statement of the positive real lemma. So the positive real lemma okay. So let GS be a transfer function, and let's assume that there is a minimal state realization of this transfer function, which is given by x dot equal to ax plus bu, y equal to cx plus du. Of course, because this is a minimal state representation, what that means is AB is controllable and AC is observable. Okay. Now, further we assume that this transfer function is stable. Okay, so GS is stable. Then the statement says that GS is positive real if and only if there exists three matrices. The first one, P, is a symmetric positive semi-definite matrix. Okay. In fact, most of the times you are talking about positive matrix, a symmetric positive matrix P, and two other matrices L and W, such that the following three equations are satisfied, and the equations are A transpose P plus P A is equal to minus L transpose L. This statement essentially says that using this positive definite matrix P and the state matrix A, you end up with this Lyapunov equation, and the resulting thing is something which is negative semi-definite. Because L transpose L is going to be positive semi-definite, and the minus sign will make it negative semi-definite. Then PB, B being this matrix B from the state representation, is equal to C transpose minus L transpose W, and the last equation is W transpose W is equal to D plus D transpose. Okay. So of course, there is also this ambiguity about what we mean by positive real, and what I had said in the earlier lecture is that for the time being, at least, we will consider a function to be positive real if Nyquist plot of that particular transfer function lies in the first and the fourth quadrant. That means the real part of the Nyquist plot is always positive. Yeah. And I had also said in the last lecture that of course this definition of positive real may not necessarily be the definition that you see in all the books. Often the definition of positive real includes the fact that it is already stable and so on, but what those intricacies are, I will come to that a bit later, and I will explain why. I mean, of course, there is no agreement as to what exactly the definition of positive real is, but I will try and explain so that it is clear to you what are the various notions of positive real that exist and how they are all related and within the epsilon neighborhood of one another. Okay. Now, in the last class, in the last lecture, what I did show is the following, that suppose we assume that there is a GS and we assume this is the minimal state representation, and we assume that there are matrices P and L and W such that these equations are satisfied, then what it means is that the transfer function results in a system which is passive. Okay. Now, the fact that passive is equivalent to positive real is something that I have talked about, but is not been completely proved. So, in some sense, what I showed yesterday along with what I will show today, that means these two conditions, that this is equivalent to this, should also prove that when you have either these matrix conditions or the fact that something is positive real satisfied, then you have a passive system. Okay. So, now let me begin the proof. So, in the beginning, let me assume, so I will prove this way, that means I will assume that there exists P, L and W such that these equations are satisfied, and I will show that the GS is stable and it is positive real. Okay. That means the Nyquist plot is in first and the fourth quadrants. Okay. Now, if you look at this first equation, this is the Lyapunov equation. Now, what we are saying is, using this A, you write down the Lyapunov equation, and with a positive definite matrix P, you are ending up with something which is negative semi-definite. Now, it is well known that this is only possible if the matrix A is Hurwitz. So, if the matrix A is Hurwitz, then the resulting transfer function is stable. So, the first equation already shows us that GS is stable. Okay. So, all that we have to do further is show that the transfer function that you get is positive real. That means its Nyquist plot lies in the first and the fourth quadrant. Okay. So, let us start trying to do that. So, for that, let me first write down what GS is. So, GS is really C Si minus A inverse B plus D. Okay. Let me use the symbol phi of S for Si minus A inverse. Okay. Now, what I want to show is the following, that G of j omega plus G of minus j omega transpose is greater than or equal to 0 for all omega. If I show this, I would have shown it for the Nyquist plot, but in fact, what I am going to do is something more general than that. What I am going to show is G of S plus G of S star transpose is greater than or equal to 0. This is roughly what I would be showing. Okay, now how to show this? So, I will write down the expression for this, and I will write down the expression for this, but I will use phi of S instead of writing Si minus A. So, this expression is C phi of S B plus D plus this expression will give me D transpose plus B transpose phi S star transpose phi S star transpose C transpose. And now what I will do is I will make use of some equations that we already have in the positive real lemma. So, in the positive real lemma we see that D plus D transpose is W transpose W, and we are assuming these things are satisfied. So, for D plus D transpose I will substitute by W transpose W. So, for this one I can write W transpose W, and there are these other two terms, and what I would do is I will use this particular second equation. For C transpose I will substitute PB minus L transpose W. Okay. So, if I do that, this particular expression becomes B transpose phi S star transpose times PB, that is one expression, plus I will have one more expression which will have B transpose phi S star transpose L transpose W. And now similarly, just like what we did for C transpose, I can substitute for C, it will be the transposes, and so these two guys will appear as transposes here, but instead of phi S star transpose, I will have phi S for those two terms. Okay, so maybe I should just write them down. So, I will get another term B transpose P transpose phi S B, and one more term which is W transpose L phi S B. Okay. So, I get these 5 terms. Now, out of these 5 terms, let me concentrate. So, there are these 5 terms that appeared. Let me concentrate just on this one and this one. Okay. So, let the other 3 terms be as they are. I will just concentrate on these 2. Okay. So, just concentrating on those 2, I have B transpose phi S star transpose PB plus B transpose P transpose phi S B. Okay. Now, I am going to do some simplification of this. So, what I would do is this particular expression I can write it down in the following way: B transpose phi S star transpose. Okay. And now, inside I introduce P times Si minus A, and remember that we have already said that this phi of S is the inverse of Si minus A. So, these two are really inverses. So, I am effectively writing this down, but I have written the first 3 terms down here, and then these two actually cancel, followed by B. And I do the same kind of thing for the other term also. And so, okay, so sorry, probably I shouldn't have done it for this one, but I should have done it for this one, I guess. Phi S. Okay, no, it doesn't matter. So, now for this one I can write plus okay, so that one is the same as this one, plus here I write down B transpose, I have the phi S star transpose, and then I have S star I minus A transpose, which is really the inverse of this. So, these two can cancel then, and then I have P. So this P transpose, because P is a symmetric matrix, P transpose is the same as P. So I'm just putting P here, and then I have phi S B. Now if you look at both the terms have B transpose phi S star transpose in the left side and phi S B in the right side. So what is inside can just be put in together, and so then what you have is B transpose phi S star transpose. Now putting the things inside together, you get S plus S star times P minus P A minus A transpose P times phi S times B. And now we again go back to the positive real lemma. The first equation in the positive real lemma say that A transpose P plus PA is minus L transpose L, and so we can substitute that in there. Okay. So if you substitute that in there, then this particular expression can be written as this particular term will give me S plus S star. These are just scalars, so I can pull them out. B transpose phi S star transpose P phi S B. So I have just used up this much, and then the other portion, so P A plus A transpose P from that first equation, that should be equal to minus L transpose L. So I will substitute that minus L transpose L, and therefore I end up with B transpose phi S star transpose L transpose L phi S B. So these two terms we picked up, and we end up with these two terms. Okay, this is a term which is sort of symmetric, if you like, but multiplied by S plus S star, and this is also something which is symmetric, but what you have is that L transpose L. Now let us go back to that previous thing where you had these 5 terms, and we picked up these 2 terms and did manipulations to get what we have there. So what I will do is, into this slide I will cancel these 2 terms, and I will add the 2 terms that we have got now. The 2 terms that we have got now are S plus S star times B transpose phi S star transpose P phi S B. That's the one term, and the other term is B transpose phi S star transpose L transpose L L transpose L phi S B. Now let's forget this particular, let me now not think about this one term, and let's look at the other 4 terms. And if you look at the other 4 terms, you see this W transpose appearing in 2 of the terms and W appearing in 2 of the terms, and so you can write this as a sum of squares. Okay. So let me just write that as a sum of squares in a fresh slide. So as a sum of squares, what you get is W transpose plus B transpose phi S star transpose L transpose multiplying W plus L phi S B. So if you multiply this out, you will get W transpose W, W transpose L phi S B, B transpose phi S star L transpose W, and then B transpose phi S star L transpose L phi S B. So you would have got this, 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 and this, these 4 terms. Now these 4 terms, and then the one other thing that we have is S plus S star B transpose phi S star transpose P phi S B. So this is the full expression that you will get, and this is the expression, mind you, when you started out with GS plus GS star transpose. This is equal to this whole expression. Now, if you look at this whole expression, this is really a square. So, if this is a square, this is always going to be positive. And if you look here, P, the assumption was that P is a positive definite matrix. So, whatever is this thing, this is something acting on a positive definite matrix, and as a result, what you have here is something positive. And if you assume that S is such that the real part of S is greater than 0, then S plus S star, this is going to be positive. So, this whole thing is going to be positive. So, what we can conclude therefore is this is greater than or equal to 0, and so effectively we have shown that this is greater than or equal to 0. Okay. So, what we have done just now is we have started in the positive real lemma, we have started with this assumption, and we have gone ahead and shown that this G S is positive real. Yeah. In fact, what we have shown is whatever I have been using as the definition of positive real, it is something slightly more than that. So, what we have really shown is, if you look at this slide, it is clear what it is that we have really shown. We have shown that G S plus G S star transpose is greater than or equal to 0 for all S such that the real part of S is greater than 0. And in fact, this should ideally be taken as the definition of positive real. Okay. The definition of positive real, in fact, rather than use S greater than or equal to, rather than use S in the imaginary axis, which means you are looking at whether the Nyquist plot is in the first or the fourth quadrant, rather than use that, it is this definition. That means, what we are really saying is that the whole of the right half plane should map under this map G S plus G S star transpose. When you are taking this map from the complex plane to the complex plane, the whole of the right half plane should map to something which is in the first and the fourth quadrant, and in that case you can call it positive real. Yeah. And so, if you use this definition of positive reality, then in the positive real lemma, in the original statement, you do not have to insist that G S is stable, because it has to be stable if this condition has to be satisfied. Okay. But these are intricacies, and there is no general agreement about what is the exact definition. So, we will leave it at that. So, what we have now effectively shown is one way of this argument. That means, assuming that these equations are satisfied, we have shown that this holds. Now, we want to show the other way. That means, if you assume G S is stable, then G S is positive real. You want to show that these equations are satisfied. Okay. Now, in order to do this, I will have to invoke some other generic theorems that are known. One of them is the spectral factorization theorem. Okay. Now, as we go along, I would talk about the spectral factorization theorem. The spectral factorization theorem is a theorem which plays a central role in other fields also, not just in control theory. So, that is something that we require, and I would also invoke a lot of things that we know about realization theory. That means, given a transfer function, how do you realize state space representation? Okay. So, let me start. So we are assuming G S is stable, and G S plus G S star transpose is greater than or equal to 0 for all S such that the real part of S is greater than 0, greater than or equal to 0. So, this is our assumption. Okay, let us look at this particular thing. Now, what this means is if you specifically evaluate this particular matrix on the imaginary axis, then what this tells us is G j omega plus G transpose minus J omega is greater than or equal to 0 for all omega. Okay. Now, what this means is that evaluated along the imaginary axis, this particular quantity on the left hand side is greater than or equal to 0, and of course, even though I have only been talking about transfer functions, these things also hold for matrices. So, even though I stated this positive real lemma, but before that I was only talking about transfer functions which are single input, single output. We can carry out, the positive real lemma as it stands is valid even for GSs which are not single input, single output. The only constraint is that this GS must be multiple input, multiple output. So, they are square matrices, the number of inputs is equal to the number of outputs, and GS is positive real. Well, there is the definition of positive reality for the matrices which I have not given, but I will give as soon as we finish the complete proof of positive real. Okay. So, whatever I have been showing holds even for the matrix case. It is not just for the scalars case, even though earlier I have only talked about the scalar situation, the single input, single output situation, but you could also look at the multi input, multi output situation, and exactly the same kind of proofs go through.